Welcome back. We're joined again with Dr. D'Antonio, and now we're being joined by Scott Green and James Lanier. Both are pre-med majors here at USCB. So we'll start with you, Scott. Can you tell us a little bit about Chagas disease and how it's transmitted?
Yes, ma'am. Chagas disease, it's one of the world's neglected diseases. It's actually a neglected tropical disease, and currently it affects about 8 million people worldwide. You know, mainly in impoverished nations in Central and South America where, you know, medical treatment is either very scarce or, you know, they don't have the money for it. And it's spread by an insect vector. It's called a triatomine insect. It's a kissing bug. And what happens is the kissing bug bites a person, and in the process of them biting a person, some of their feces actually get into the bite wound, and the parasite, Trypanosoma cruzi, is what is inside of their feces, and that's what gets into your body, and it starts to get into your bloodstream. It starts hijacking cells and feeding off of blood glucose. So basically, in the acute stage, some of the symptoms you can see are, you know, localized swelling. You can get stinging pains in your fingertips. You can have diarrhea, and as you move into the more chronic stages, you end up getting, you know, as these things start to build colonies in the soft tissue around your organs, you can end up with cardiomyopathy, enlargement of the heart. You can end up with a megacolon. You can end up with a megaesophagus. Very uncomfortable, and basically, you know, it affects a person based on their overall health.
Which generally people in impoverished areas don't have the best health to start with.
Exactly. So, you know, and then if you have someone who's really young, who doesn't really have the developed immune system yet, or you have someone who's older, who maybe have a more weakened immune system. And so basically in the last, since the early 1970s, there hasn't really been a whole lot of progress on this. There was 2 drugs that were developed in the early 1970s. They were called benznidazole and nifurtimox. And basically, they're both called prodrugs, and so basically what they do is they go into the body as an inert drug, and they pass through cells. Once the drug actually finds the cell that contains the parasite, it activates, and it kills the cell, but it also becomes toxic to the body. And so,
problem.
Yeah, it is. You know, I mean, the idea is to make a medication where, you know, you're going in and you're harming the bad cells, and you're leaving the good ones alone.
Stuff. Yeah.
So there's a real need right now to develop new drugs that are going to be selective in that way, to go in and, you know, take care of all the bad stuff and leave all the good stuff alone, so that the person's only symptom is, you know, they feel better.
Right.
So basically what's happened is Dr. D'Antonio has identified a metabolic pathway that targets this parasite and kills them. And by a process that we call structure-based drug design, we can basically take the first step in this metabolic pathway, and if we can kill the parasite right there, then it stops the cycle.
That's impressive.
So it's really interesting, actually. Yeah.
That's amazing. I love that kind of stuff. But well, you mentioned the structure-based design with Dr. D'Antonio. What is involved in synthesizing and testing all these new compounds? I mean, this sounds incredible. It doesn't sound. It is incredibly detailed, very intense information here right at USCB, which I think is a very valid point to make.
Well, well, structure-based drug design, okay, this is just a technique of drug discovery that actually falls under an umbrella of another technique called X-ray crystallography. And our lab uses this technique called X-ray crystallography, in which I have students purify proteins to almost 100% pure. And then what they're going to do is they're going to grow a protein crystal. So from solution to the solid state, you can observe a crystal of the protein under a microscope. Now this protein crystal is going to be that of the enzyme that's found inside of Trypanosoma cruzi. That's going to be called our drug target. Now if we can get that crystal grown, we send the crystal out to a national laboratory in Chicago. It's called the Argonne National Lab. Also, there's the Advanced Light Source. And I have a collaborator there. She mounts our crystal in front of a beam line. And with the click, of a mouse on her computer, she opens the shutter of the beam line, and X-rays fly through and they hit the crystal, and then you get an X-ray diffraction. we take the diffraction and we can take that data and build a three-dimensional structure at the molecular level of our protein. By having the vision of the three-dimensional structure of our enzyme, we can then use structure-based drug design where I know what the inside of the enzyme looks like. I know the interior. There's a microenvironment. Enzymes catalyze reactions. So what we try to do, we want to get an inhibitor that we could design that's going to basically sit in there and just make contact. And if we can do that, the metabolic pathway of glycolysis would be, the flux would be constricted, thereby leading to apoptosis of the Trypanosoma cruzi.
That's kind of amazing. And I'm sure there are some people that are like, what did he just say?
Well, now, James, you're one of the students who's helping Dr. D'Antonio with this research, you and Scott. Can you tell us what some of the compounds you're currently working on and how you attempt to synthesize and purify them?
Well, instead of like just kind of spewing off a bunch of names that nobody knows, I'll tell you kind of like the process. Okay. The overall goal is to create a glucosamine analog inhibitor. And what we've done to create this is we went and we bought 7 commercially available acyl chlorides. And what we're doing is we're taking our glucose molecule and we're binding it to our glucokinase. Now, what that pretty much means is we're taking our glucosamine molecule and we're reacting it. We're going to react it with one of those 7 acyl chlorides that we bought. So then the hope is that it's going to strongly bind to the enzyme.
Yes.
And so that's pretty much the synthesization process.
Okay.
Now, for purification, once we synthesize it, we have like a bunch of leftover, like there's the things that we use to synthesize it. So there's all kinds of byproduct. So we have to purify it. We have to get it down to that last, the nitty gritty. Because if we have all this extra stuff, that's not what we want. That's not our compound. Now, once we get it, we have to put it through our high performance liquid chromatography machine. Ours is god awful old. It is so old, but I mean it works. It works. It just doesn't have all the bells and whistles, but it does its job. Now, whenever we put it through this machine, we get a little graph and we get a peak. Whenever we see that peak around maybe 20-25 minutes of putting it through our machine, it's a rush. It really. I mean, for me, I don't know about it. If someone were to look at this graph, they're like, "Oh, that's just like something going up." No, for me, that's huge. That's our compound coming out. So it's really exciting. One time, I ran out and I knocked on Dr. D's door. I was like, "Man, we just got this awesome compound." You have no idea. But anyways,
Hero peak.
yeah, we call it a hero peak. It was great.
Yeah,
but anyways,
that was a big one.
yeah.
Well, I think the moral of the story is that you guys are making amazing research. And I think a lot of people may underestimate our little USCB campus, but I think it is proof that it is growing.
Yeah, absolutely.
And that if you need more information, please visit their website. There are many programs and it's growing quickly. So thank you all for joining us, and make sure that you join us next time on 843 TV.
Where communities come to speak.